This portion of our project is about the Babylonian solution. It's a bit different than the conventional solution to quadratics that we teach in high school, but I think it's very useful, especially because factoring can be a challenge to some students, and this method does not really involve too much factoring. So a little bit of background is that the Babylonians solved, well, firstly, this is a tablet of the Pythagorean triples. Not all of them, since there's infinitely many, but some of them that the Babylonians figured out. But when they came up with this method, apparently in their writings, there's no variable representing an unknown. It was more just wording describing how to do the method, which I think is really interesting that they were able to share this without a variable and have other people be able to replicate it. But eventually later on, people were able to apply this method with the use of a variable, making it a lot easier and more translatable. Here's a visual representation. Let's start with step one. So you can adjust the size of the boxes. This method just shows how the quadratic formula can be shown geometrically. So we have our square and rectangle. Okay, the rectangle gets divided in half and situated on either side of the square. So here it asks the missing area, the area of the missing square, which is this little area right here. And the expression for the area of the large square, which is including the missing square. And then the area of this, which is the area of the large square, subtracting the area of the missing square, which gives you something like this down here, x squared plus b over a x. And you'll see when we do an example of the Babylonian method that this setup actually occurs when we're solving an actual example. Okay, so first I'd like to try an example where the coefficient is 1. So for example, if I had x squared plus 7x plus 10 equals 0. So with this method, instead of factoring in the traditional sense where we try to figure out what two numbers multiply to 10 and add to 7, it's more like completing the square where we move the constant to the other side. So now we can factor out an x. Okay, so here I'm going to make a little number line with x on the left and x plus 7 on the right. And we know that this quadratic is going to be centered right in between these two at the midpoint. And the midpoint would be x plus 7 over 2. Okay, so from here, we're going to reassign variables. The middle we will call a, and then the left side would be a minus 7 over 2. This would be a plus 7 over 2. And we can say that a minus 7 over, Alrighty, my computer glitched, so I had to restart, but here we are. I'm going to rewrite x as a minus 7 over 2 and rewrite x plus 7 as a plus 7 over 2 equals negative 10. Oops. Okay, so this would be x or a squared minus 49 over 4 equals negative 10. A squared equals negative 10 plus 49 over 4. So a squared equals 9 over 4. A equals 3 over 2 plus or minus. Okay, so we still have to go back and plug it in. Okay, so we do have to go back and plug it in to solve for x. We have a equals x plus 7 over 2. So x plus 7 over 2 equals a, which is plus or minus 3 over 2. X equals negative 7 over 2 plus or minus 3 over 2. So x would be negative 4 over 2, which is negative 2. And negative 10 over 2, which is negative 5. So those would be our two solutions. Okay, so now we're going to try the Babylonian method when there is a coefficient other than 1 of the x squared term. So this would be beneficial for students who are not great with factoring when there's a leading coefficient other than 1. It's not a shortcut by any means. There's still quite a few steps to this method, but at least the students who struggle with factoring will be able to avoid thinking about what two numbers multiply to what and add to what and splitting the middle and those steps. So if they follow the same series of steps for the Babylonian method, they'll get an answer every single time. For the leading coefficient, we are going to divide it out of every term. So I have x squared minus 5 over 2x minus 3 over 2 equals 0. We are going to move the constant to the other side. We are going to factor out the x. And make a number line. We'll have x minus 5 over 2 on the left side, x on the right side. And in the middle, we have the midpoint of these, which is x minus 5 over 4. Reassign the variables. So x minus 5 over, well, firstly, I'll make the middle a. The left side will be a minus 5 over 4, and the right side will be a plus 5 over 4. So we will replace x with a plus 5 over 4 and x minus 5 over 2 with a minus 5 over 4, which will give us a difference of squares. So a plus 5 over 4, a minus 5 over 4, which will equal 3 over 2. Okay, This will be a squared minus 25 over 16 equals 3 over 2. A squared equals 3 over 2 plus 25 over 16. Shoot. So we have A equals, that would be 24 over 16 plus 29 over 16. A equals plus or minus 7 over 4. Recall that on our table we have A equals x minus 5 over 4. So I will say that x minus 5 over 4 equals plus or minus 7 over 4. X equals 5 over 4 plus or minus 7 over 4. So x equals 12 over 4, which is 3, or x equals negative 2 over 4, which is negative 1/2. So there are our two solutions. So now I will be showing one real-world example of a quadratic and what a quadratic is versus a catenary. So here we have a suspension bridge, which is more closely related to a quadratic. The difference being in the shape of the curves. They're both a U-shaped curve, but the quadratic's weight is more evenly distributed. There's a lot of physics concepts in here that I'm just learning about myself through this project. But they set up a point on our quadratic and model the weight using vectors and rearranging the vectors into a triangle like so. Okay, with this point here at the corner of F sub P and W being the point on the quadratic, and states that that point has the slope W over T. So if I have my quadratic like this, and my point here, we have this called W, and this is called T. Okay, so that's how you get the slope formula, rise over run. Now, in this next step, they define a mu, multiplying mu by the length of any interval on the deck will give the weight of that interval. So replacing W here with mu times x. So our new slope formula is now P equals mu x over T. And then it defines this point P as a function of y prime. So let y be the height of the cable, the slope of the cable then must be the first derivative of y. So P is replaced with y prime. Y prime is mu times x over T. And we take the antiderivative of y. to solve for y, and you get a function like this, which models a quadratic. So it says here that C is centered at the origin, and so C would be 0, so then we just have mu times x squared over 2t, which is our quadratic function that models the suspension bridge. Now, as opposed to catenary, catenary, the weight is not evenly distributed like a parabola, but more in the center, and is modeled by a different equation that is not a quadratic. There's no parabola that would perfectly overlap with a catenary. So here it says a parabola describes the motion of a projectile thrown into the air, disregarding air resistance. So it's more of a smooth U, whereas a catenary has a little bit more weight, especially in the middle. And here it shows how to derive the equation of a catenary involving some calculus and differential equations. So it goes here, and here's a GeoGebra that I made, showing some real world examples of catenaries and the corresponding equations. So as you move the slider, a picture will appear. So here's the gateway arc modeled by this equation, and some other real world examples. Here's the Golden Gate Bridge. Now, some websites were saying that the Golden Gate Bridge is modeled by a catenary, and some were saying that it's modeled by a parabola. I couldn't get a clear answer on this, but in this picture, well, this is cartoon, but it models, it goes pretty well with the catenary, I would say. Spider web, and I have some chains. Where did they go? A silver chain. I just found these pictures off of some jewelry websites. And yeah, so those are the differences between parabolas and catenaries.
Junet Leon, thank you for watching our presentations of quadratic equations. Let me try and pin this over here. So a little history on quadratic equations. It is claimed that the Babylonians, about 400 BC, were the first ones to solve quadratic equations, even though the Babylonians really had no notion of what the term equation as we use it today. What they did develop was an algorithmic approach to solving problems, which in our terminology will give rise to a quadratic equation. The method is essentially one of completing the squares, what the Babylonians used. However, all the problems at the time of the Babylonians had answers which were positive, or more accurately, unsigned quantities, since the usual answer was a length. In about 300 BC, Euclid developed a geometrical approach, which, although later mathematicians used it to solve quadratic equations, it amounted to finding a length, which in our notion was the root of a quadratic equation. Euclid had no notion of equation or coefficients, etc., but worked out with purely geometrical quantities. Hindu mathematicians took the Babylonian methods further, so that Brahmagupta, around 598 to 665 AD, gives an almost modern method which omits negative quantities. He also used abbreviations for the unknown. Usually the initial letter of a color was used, and sometimes several different unknowns occur in a single problem. The Arabs did not know about the advances of the Hindus, so they had neither negative quantities nor abbreviations for their unknowns. However, Al-Khwarizmi, around 800, gave classifications of different types of quadratic, although only numerical examples of each. The different types arise since Al-Khwarizmi had no zero or negatives. He has 6 chapters, each devoted to a different type of equation. Here on the right-hand side, there's a picture on the topic of these 6 chapters. The equations are being made up of 3 different quantities: roots, squares of roots, and numbers. The quadratic formula and Pauli-Loew's derivation. The quadratic formula was a remarkable triumph of early mathematicians, marking the completion of a long quest to solve quadratic equations. With a storied history stretching as far back as the Old Babylonian period, around 2000 to 1600 BC. In 2019, only 3 years ago, Dr. Pauli-Loew from Caltech University published a method for finding the roots of a quadratic equation, without the need for factoring or the arguably tedious to remember and use quadratic equation. His method was based upon known ideas at the time, but had never before been expressed as a comprehensive algorithm as he did. Dr. Pauli-Loew's method uses the idea of the 2 roots of every quadratic equation to make a simpler way to derive those roots. He realized he could describe the 2 roots of a quadratic equation this way. Combined, the 2 roots average out to a certain value, which is negative b from the standard form of the equation, the opposite of b, coefficient of the linear term. Then there's a value u, a distance that shows any additional unknown value from this middle point. In other words, the axis of symmetry of the parabola. So u will be the distance to the right and the left of the axis of symmetry, where we would find the zeros. So instead of searching for 2 separate different values, we're searching for 2 identical values to begin with. This simplifies the arithmetic part of multiplying the formula out. Okay, so let's see over here. Okay, so normally when we do a factoring problem, we're trying to find 2 numbers that multiply to the b term, that multiply to the c term and add up to the b term in the standard form of a quadratic equation. So the standard form of a quadratic equation, y equals ax squared plus bx plus c. So we're looking for 2 numbers. Let's call those numbers r and s, where r times s equals c and r plus s equals b. And those are the coefficients. C is the constant, a and b, the coefficients of the square and the linear term. So those 2 numbers will be the solutions of the quadratic equation, or the zeros, or the x-intercepts of the graph. So this method, it can take students a lot of time. Sometimes it can take them, for algebra beginners, it can take them a lot of time to solve for them, or it can just be, a bit of a guess and check kind of approach. So instead of starting by factoring the product c, Dr. Lowe's method tells us to start with the sum, b. If the 2 numbers we're looking for added together equals to b, then they must be equidistant from their average. So, in other words, so if we have, let's say, b is going to be, in this case, negative b, is going to be the axis of symmetry. For the axis of symmetry of the equation, that will be y equals negative b over 2a. So that value, let's say whatever that value is, we would have a certain distance to the right of that axis of symmetry and the same distance to the left of that axis of symmetry. So we have, in this case, where if a is equal to 1, then our numbers, our 2 zeros will be at, let's see, that's right over here, at negative b over 2 plus that distance u. That'll be one of the zeros, and the other zero will be negative b over 2 minus u. Okay, so the product of the two numbers, also we know the products of the two numbers have to be equal to c. So we have negative b over 2 plus u times negative b over 2 minus u equals c. So here we have the sum and the difference of two binomials. So the two middle terms cancel out when we multiply, and we get the difference of the two squared. So that is negative b over 2 squared minus u squared equals c. When we solve for u over here, which will be the distance, we get that u equals the square root of b over 2 squared. We can just write b over 2, even though it's negative b because that's being square. Actually, let me just put the negative here, minus c. So the two solutions will be negative b over 2 plus or minus, this is the axis of symmetry, plus or minus this distance, the distance u. So negative b over 2 squared minus c. And it looks really here a little bit more complicated, or a lot more complicated than it really is. So let's look at an example. Okay, so let's first do an example where a equals 1. So we have y equals x squared plus 4x plus 3. So traditionally in a classroom, we would, start trying to factor this, and we can easily factor this this quadratic polynomial here. We're looking for two numbers that multiplied together are 3 and added together are 4, and those numbers will be 3 and 1, right? So we have x plus 3 and x plus 1 are the two factors, and that means the zeros are then is the opposite of that. So the zeros are negative 3 and negative 1. Okay, now let's say that it was really wasn't as simple to factor. At that point, we would use the quadratic formula traditionally, which it does usually. As math teacher, I have seen how much students struggle doing, using the quadratic formula correctly, with the order of operations, keeping their signs correctly. So Dr. Lowe's method actually takes a lot of that away. It is a lot simpler to do it accurately. So using Dr. Lowe's method, what we would do is first we can calculate the axis of symmetry. So the axis of symmetry is given by negative b over 2a. In this case, that is negative 4 over 2 times 1, which is negative 2. So then we're going to look for that u, the distance to the right and to the left of the axis of symmetry. So the axis of symmetry is at negative 2. The distance will give us the two zeros on the left and the right, symmetrical across the vertical axis. So we have that negative 2, r, it will be negative 2 plus u, and s is going to be negative 2 minus u. The product of r and s is equal to c. So negative r times s equals c. Negative 2 plus u times negative 2 minus u equals 3 in this case. We multiply this out, and we have 4 minus u squared equals 3. This is u squared equals 3 minus 4 is negative 1. The opposite of that is positive 1, so u equals 1. So this means, going back over here, we have that r equals negative 2 plus 1, and s equals negative 2 minus 1. So this is negative 1, and then s will be negative 3. So our zeros will be a negative 1 and negative 3. And over here, we can see this. I have this equation over here. I have the graph. We have the graph here of y equals x squared plus 4x plus 3. Negative 2, here's the axis of symmetry, and the zeros, x-interceptions are negative 1 and negative 3. Now let's look at this other example where now a is not equal to 1. So now we have, we're going to look at y equals y equals y equals negative 2x. I'm sorry, what's the negative? Let me do this. Put this to the left. Okay, so it is y equals not negative 2x, y equals 2x squared minus x minus 3. So first we're going to factor out that 2. So we're going to divide by 2, and we have y equals x squared minus 1/2 x minus 3 over 2. So now we're going to treat it like we did the previous example. So we have the axis of symmetry is given by negative b over 2a. A is already 1 now on this one that we are this equivalent equation. So we have y equals 1/2 divided by 2, which is equal to 1/4. So r, one of the roots is going to be given by 1/4 plus u, and the other one by 1/4 minus u. So we are going to find the value of u. We use the fact that the two numbers multiplied together, it's supposed to be an s, are equal to negative 3. So we have 1/16 minus u squared equals negative 3. That means u squared equals negative 3. I'm sorry, not negative 3. C is negative 3 over 2. So u squared will be negative 3 over 2 minus 1/16, opposite of that when we divide by that negative 1. So we get u squared equals negative 25 over 16. That means u equals 5/4. That's u is a distance. U is the distance from the axis of symmetry to the 0, so it's a positive number. So that means r is equal to 1/4 plus 5/4, or 1/4 plus 5/4, which is 3/2, and s is equal to 1/4 minus 5/4, or negative 1. So these are the two roots, and over here we can see the graph for this equation, y equals 2x squared minus x minus 3. The axis of symmetry goes through 1/4, and we have the two zeros at 1.5 or 3/2 and negative 1.